In this section, we're going to talk about derivatives, define a derivative, talk about rates of change, instantaneous velocity, and cycle all the way back to how we started the course when we were talking about instantaneous velocities and slopes of tangent lines. So we're going to revisit, now that we've built up our skills around limits, we have a toolbox full of ways to compute limits, we are going to cycle back to those original problems that we looked at and apply our limit knowledge to those. So just to remind you, early in the course, we looked at a function and we said, what if we wanted the tangent line at a point? And so let me zoom in on this guy right here. What if we wanted a tangent line at a single point? So we wanted to know right exactly at a point P what the function was doing. And so when we did that, we said, well, the easiest way to do that, this being the tangent line, the easiest way to come up with the slope of a tangent line, because we don't have a tangent line, there's only one point on the curve, and that's not enough to write an equation of a line or come up with a slope. So if we wanted the slope of that tangent line, and that tangent line just touches the curve at that point, what we end up having to do is we have to say, we actually have to go over to another point over here on the curve, we called it Q, and we have to look at the slope and the behavior of the secant line through 2 points. And then what we did, if you remember, is we moved that point back in closer and closer and closer until the secant lines that we were looking at could be used to estimate what the tangent line was doing. We made them get so close to the tangent line that they were approximating the behavior of the tangent line at a single point. And we use tables to do that because that's the techniques that we had at that time, at the very beginning of this course, at the very beginning of this chapter. But now we have more techniques. And back then in the introduction, I even used this notation a little bit, but we are going to get into it and use it a lot more because we know how to use limits now. So now what we're going to define is we're actually going to say this. We're going to say if we wanted to find the slope of a tangent line, what we're going to do is we're actually going to let that point Q approach that point P of the secant lines, and that is going to give us this formal definition here, the limit as x approaches a of f of x minus f of a over x minus a. So let me take you over here to a little graph and show you where that comes from, and then we will formalize it with a definition. So here we are at our point P. We're going to call that point, or we know that point is going to be at A. We're going to define it to be at A for a function. So this is the point A, f of A. And we're going to come a little ways off. We want the tangent line at this curve, but to find the tangent line at this curve, right, the tangent line is the line that just touches the curve, represents the behavior of the curve if we were to zoom way in on it. So this is the tangent line at that curve. This is tangent to the curve at that point. So tangent at P, at A, f of A. That's the tangent line, but in order to find the slope, we need to do a secant line. So we come over here, we call this point Q, and we're going to let that point just be at some x. So this is going to be at x, f of x. And we could draw the secant line, and the secant line is going to be the line that goes through those 2 points. So that line, oops, I moved my slide after I lined up my ruler. So that is the secant line. Now the secant line is going to move because we are going to let Q get closer to P. We're going to actually let X approach A. We're going to march our X's in towards A here. And so if we think about how you actually compute a slope, let's do the secant line first. The slope of a secant line, it's just the difference of the Y's over the difference of the X's. So that's just f of X minus f of A over x minus a. So just taking the difference of the y values, we've got our 2 ordered pairs, and we're just taking the difference of our y values, f of x minus f of a, over x minus a, difference in the x's. So just definition of a slope, little algebra right there. So that's the slope of our secant line, but we are actually going to do this. We're going to say we want to find the slope of the tangent line. So the slope of the tangent line is going to be equal to the limit as, and I'm going to write it this way, the limit as q approaches p, because we are going to move that q closer. We're going to just pick closer and closer and closer values, continuing to let q get closer and closer to p. So that's actually when we, in our second line, we're going to say that's as x approaches a. So we're going to say here as q approaches p of the slopes of the secants, but that is going to give us this definition. So the slope of the tangent line is actually going to be the limit as x approaches a of f of x minus f of a over x minus a. And that is where we get that formal definition. I introduced this limit notation for the very first time, the first time we looked at these slopes, but we didn't have the tools to really use the limit notation. We saw it then, but we didn't use it. We used tables and so forth, and estimates to do this. So now we're going to come back and we're actually going to formally define this slope of the tangent line. That instantaneous rate of change, that's another way to say that. That is the instantaneous rate of change. A slope is a rate of change. So always remember this. By the way, let's keep this up here. A slope is a rate of change. Now, you know, if we have context, it's a change in the y, whatever the y is representing. It's a change in the output or the y values over the change of the x's or the input values. But it is always a rate of change. So a slope is a rate of change. So when we look at an instantaneous rate of change, right, at a single point at a tangent line, we're looking at that slope of the function in that instant that it hits that point P, right at that point. It's that instantaneous rate of change, or that slope of that tangent line right at that point. If we could just zoom in infinitely close to that point P, we would see this behavior as behaving like that tangent line, the behavior of the function. All right, so here is our official first definition coming out of that graph and that Q approaching P, looking at the secant lines. And we can see I typed it up here. This would be a good time if you wanted to freeze the screen. Freeze the screen and take this down in your notes, because this is our first definition for the slope of a tangent line to a curve, or a rate of change. So again, the average rate of change, which is coming out of that secant line, is that first line. The slope of the secant lines are f of x minus f of a over x minus a. But that excuse me, that instantaneous rate of change, also called the slope of the tangent line, at a point is given right here. That instantaneous, and I'll highlight that to make it really, really very bold on this page. That instantaneous rate of change, the slope of a tangent line to a curve at a point, is given this way. This is our first definition of it. We're actually going to have two definitions of this, really just a slight variation on the variables, but we will have two definitions. So we will call this definition 1. We label this definition 1. That corresponds with our textbook, our Stewart textbook, but we'll call this our definition 1 for the slope of a tangent line, and it's given this way. We will have to spend a little more time thinking about this part. I will add it in right now, but we're going to work on the mechanics first. This is when this limit exists. Of course, if this limit doesn't exist, we're going to have to talk about what that means. What does that mean about the tangent line and the function? But for now, this is our definition, and we will have that qualification that when this limit exists, this is how we define the tangent line. Now, this piece down here is algebra, because once you know the slope, you can find the equation of a line. So here is the equation, but finding the equation just involves some algebra. So finding the actual equation, once you have the slope, finding the equation of a tangent line is algebra. So that is just some algebra. So once we've got the slope, which we're going to use the limit to find, we will then just use some algebra to find the actual equation of the tangent line. I will highlight it though, because once we have that slope, we'll want to use point slope formula or however you want to find it, but you will need to find the full equations. We'll want to actually know what those equations look like, not just the slopes sometimes. Okay, I'm going to leave that up on the screen, freeze it if you need to, but definitely get that down in your notes, because you will be asked to use definition 1 and or definition 2, but you'll want to know that this is definition 1. And then we're going to do some examples. All right, so let's do this. Let's get in here and let's find the equations of some tangent lines at specific points. So here we're going to start with x cubed. And by the way, we know what x cubed looks like, right? That's just this cubic function. Let's see, it's at 2, 8, so I want to make sure I get my scale here. There's x. There's 8 and 1 and 2. It's going to pass through 1, 1, and at 2 will be up here, here, and we know we've got a graph of a cubic, and it looks something like that. And we are focused in on this point right here at 2, 8, and we want to know what the slope of the, not just the slope of the tangent line, but what is the equation of the tangent line. Now, to find the equation of any line, the first thing you need is you need to find the slope. So find the slope first. Okay, that will be our first thing. So we need to find the slope of the tangent line. Now, I didn't specify actually here because at this point in the video, we only have one definition, but I will put this at the top here. We will use definition 1. Okay, so we want to use definition 1. Sometimes I refer to definition 1 as the x approaching a definition, just to clarify which definition. But definition 1 is the definition that uses the limit as x approaches a. Our second definition will be slightly different, so we'll have that in a moment. Okay, so let's find the slope. So the slope of the tangent line is defined to be the limit using this definition. So it's defined to be the limit as x approaches a of f of x minus f of a over x minus a. So I'm just rewriting it here since I have a small screen and we don't have the actual definition up on the board. So that's the definition. That's what we have to use. So we're going to get in here and we're going to say, all right, so the slope of this tangent line for this one, m sub tan, is going to be equal to the limit as x approaches 2. So, you know, if you want to think about this visually and graphically, you're thinking about this is your point P right here. So this is your point P, and we're picking another point off, actually on both sides. We want to think of x approaching 2 from both sides, but we're picking another point and we're marching it in towards 2. So x approaching 2, so as x approaches a, this is our a value, a f of a. That's our specific point that we're given. So the limit as x approaches 2 of f of x, well, our f of x is x cubed, minus f of a, well, our f of a value at 2, this function 2 cubed, I'm going to write 2 cubed just so we see it. 2 cubed would be 8 over x minus 2. Okay. And then we're just going to, now we're going to use limits, right? Like at this point, just use limit techniques. So we get to practice all the things that we've been doing. So we're going to use our limit techniques at this point. We're going to take this limit is, I'm going to simplify first, limit as x approaches 2. We've got x cubed minus 8 over x minus 2. Using our limit techniques, remember what we've done is we tend to try direct substitution, and if I try direct substitution, notice I get that 0 over 0. So this is what I mean by, you know, use our limit techniques. That always means do more work. So we're going to get in here, we're going to think about the fact that if we have a 0 over 0 and we have a rational function here, which is what we've got, x cubed minus 8 over x minus 2, we would want to try factoring to see if we can cancel a common root. And so let's see what happens here. Limit as x approaches 2. That's a difference of 2 cubes, so I can factor that, x minus 2, x squared plus 2x plus 4, all over, and I'm just using the difference of 2 cubes formula. Okay. Factors into a binomial and a trinomial. And on the bottom, of course, I have x minus 2. Okay. And there it is. There's that canceling we were hoping for. And this is now the limit as we approach 2 of simply x squared plus 2x plus 4. And now we can fully use that direct substitution. So now we can plug that in. That's going to be 4 plus 4 plus 4. So we end up with a limit value of 12. Well, what is that? Remember, now we're not just finding limits, we're using our limit tools, our limit techniques in order to find the slope of a tangent line. So that is the slope of the tangent line. So the slope of the tangent line is 12, which if you want to think about it, right, like if we're thinking about actually graphing here, This is a very steep, I mean, it's almost based on my scale, almost looks kind of vertical here, but it's not. It has a slope of 12, so the slope of this tangent line, like right in here, if you get in here, the slope of this tangent line, and that's probably not the best line right there, but the slope of that tangent line right at that point does have a steep slope, right? At even at 2 for a cubic, we've got a pretty steep slope. Has a slope of 12, meaning rise over run, 12 over 1. So this does have a pretty steep slope. Now remember, that wasn't all we wanted to do, right? We needed to find the slope first, but then we're going to write the equation. So now let's get in there and let's actually write the equation. That again, I will remind you, is simply algebra. So we're going to get in here. The second step is to then write the equation. If we were asked for the equation, sometimes all we want is the slope of the tangent line, but we want the actual equation of the tangent line. So we'll finish this out by finding the equation of the tangent line. Again, we know the slope, so given the slope is 12, right, we can do this in a couple different ways. You could write just y equals 12x plus b. That's just using the slope-intercept form, and then we know that it passes through, or the ordered pair that we're looking at is going through 2, 8. So then I just plug that in. So 8 equals 12 times 2. Now let's see here. So 24, and b is a negative 16. Okay, put that together and the actual equation of my tangent line. Y equals 12x minus 16. And there is my answer. Okay, let's finish off with one more example. So if we wanted to look at 1 over x, and again, I grabbed for these first two ones that we should be able to actually just graph if we wanted to. Without using technology, we should know what 1 over x looks like. So 1 over x is the rational function with a vertical asymptote at 0, and it has this shape. And we want to find the actual tangent line at 1, 1. So if we were to bring our ruler in, the tangent line at 1, 1 would be this, something like this. Now it's not a perfect graph, but we get the general idea. So there's our tangent line. So we want the equation of that tangent line to this curve 1 over x at 1, 1. So that's what we're looking for visually. So how are we going to do that? Well, the first step is to actually find the slope of the tangent line. So we want to find the slope of the tangent line. To find the slope of the tangent line, for these two examples, I want to use our first definition, since that's the only one we have right now. A slope is the limit of f of x minus f of a, and this is our slope formula, f of x minus f of a over x minus a, as x approaches a. Remember, this is always just slope formula. We're really just putting together pieces that we have from our previous knowledge now to attack a problem about slopes of tangent lines. So here we are. So it's a slope formula, but we're letting x approach a because we have to first look at secant lines, and we can do that for this specific function. Our a value here is 1, and our f of a value, of course, is also 1, because when you plug 1 into this function, you get 1 over 1. Our function itself actually is g, so I shouldn't write f of a, I should write g of a. So this is g of a. And we'll be working with, rather than f of x, we would want to work with g of x and g of a. Okay, that was the definition. The f of x definition is our generic definition, but now we're applying it to a specific function, g. So let's get in here. So the limit as x is approaching 1, g of x is 1 over x, minus, now when we plug in 1 here, this would be 1 over 1. Now we already know that's 1, but I'll write it there so we can see it, over x minus 1. And now we end up with a limit, and we have to apply our limit techniques. Now, again, we always kind of try for that direct substitution, and notice that we get that 0 over 0, which just means to us that we got to do more work. But again, we're going to have to look at the type of function we have here, and we have a compound fraction, fractions and fractions. So I would say the first thing to do here, of course, would just be to simplify. So get in here and see if we can get this simplified. I notice on the top here that I could find a common denominator, so multiply by x over x, and I would have 1 minus x over x in the top, and then in the bottom, I have x minus 1. I have the quantity x minus 1. So this, by the way, x minus 1 over 1, and then I have I'm dividing a fraction by a fraction. So this is the same, and I'm going to just use, I'm just using algebra here to simplify this. I'm just saying, well, to continue to simplify this so that I can actually take the limit, I'm going to take 1 minus x over x, and since I was dividing by x minus 1, that's the same as multiplying by 1 over x minus 1. And then I notice that these two polynomials, I didn't meant to highlight, not cross that off. These two polynomials are equal and opposite in sign. So I could do a nice little algebra trick and pull out a -1 from this first one. If I pulled out a -1, this would become x minus 1. And then I can cancel my x minus 1s and my x minus 1s, but I will be left with that -1. So keeping in mind that little, when you have equal and opposite polynomials like that, you can factor a -1 out so that you can cancel. Now in the numerator, I end up with -1 in the denominator, just x. And now I can take that limit because now I can use direct substitution. I won't end up with division by 0. Plug in 1, I get -1 over 1, which is -1. So that means that the slope of my tangent line at that point is equal to -1. And that's the first step in finding the equation of the tangent line. That should make sense based on our graph. A negative slope, we didn't even talk about it on the other one. We did talk about how on x cubed we had a steep slope. But here at this graph, it should absolutely be a negative slope. The function is decreasing. A negative slope is a decreasing line or decreasing behavior as we move from left to right, and we do have a negative slope. So then now we're going to find the actual equation of the tangent line. So to find the equation of the line, the tangent line, you can use any algebraic technique for finding equations of lines. On the last example, I simply plugged into our slope-intercept form. So here I'll just show a different way. I will show, this is called the point-slope form. So this is point-slope form, and some of you are probably familiar and use this technique. So using the point-slope form, we simply plug in our point, which is 1, 1. So it will be y minus 1. And then we plug in our slope, -1, and our x value of our point, which is 1. So we plug that in, and then we simplify. Y minus 1 equals -1 plus 1. Add 1, and we get y. Oh, I lost my x. -1x plus 1. And then we get y equals, just by adding 1 to both sides, we get y equals -x plus 2. And that is the equation of my tangent line for this second example, using our first definition for the slopes of these tangent lines, these instantaneous rates of change on a function.